think it's a good time to start. Thank you for coming on, and then I'm so happy to introduce Bogdan, and then also thankful that he accepted the invitation to our colloquium. The pleasure to introduce Professor Bogdan Petrenko from the Eastern Illinois University, and then he's working on the algebra and number theory, and then more than that. And then he's talking about today the smallest number of generators and densities of generating sets of an algebra finite over the integers. So please welcome the Bogdan.
Thank you very much. It's a beautiful campus and it's a beautiful drive, and thank you so much for inviting me. It's very nice of you. And so I will talk about some things about matrix algebras over ordinary integers that we discovered. So our matrices will only be of size 2 and 3. So it turns out they already have some interesting properties, and we obtained some results that can actually be formulated. For example, we know what are the chances if you choose several either 2 by 2 matrices or 3 by 3 matrices, what are the chances you generate the matrix algebra over integers. I was thinking if I could remind us about some basic definitions, and please bear with me, I hope it will not be too boring. I want to be sure that the terminology is understood, because in algebra there are many definitions. In fact, according to Serge Lang's book, it's the biggest difficulty in studying algebra, right? There's many definitions, right? I mean, that's what he writes in the preface to his algebra. So let's suppose R is associated community ring with 1. And what is nice is that our work gives new information even over integers. So for this talk, this ring be the ring of integers, even though in the paper we talk about orders and number fields, maybe let's see if we can say something new about ordinary integers, high school integers. And so another piece of notation, smallest number of generators of A. Sometimes, very rarely, we specify over what ring is the smallest number of generators of A as an R algebra. And we will assume that the additive group of our algebras, this additive group, is finitely generated. So we want to introduce the following definition. So I will say, I'll put it here, say definition 1. So a set S generates R algebra A if A is the R linear span of all monomials in S of degree 0 0 or more. So all possible monomials. So S generates our algebra if we allow the identity element inside the generating set. Now, S strongly generates A if the same holds except the very end. We don't imply that we include the identity element inside among the generators. So let me write down a couple of examples. I should have asked earlier, is there any glare on the board? Can you see well? Okay. So let's do first example. So suppose we look at the matrix E12, which is 0, 0, 1, 0, and E21, which is 0, 1, 0, 0. They generate any algebra, say, of R, because of the fact that E11 is E12, E21, and E22 is so, and since any matrix is a linear combination of these four matrices, we have generation here. Now, what's interesting is example 2 is already interesting. If in the algebra, suppose we take a direct product of several matrix algebra, all the sizes are at least 2, then any set that generates also strongly generates it. So in other words, if we look at products of matrix algebras, it turns out that two definitions are equivalent, and therefore we don't have to make this distinction. Do we allow the identity element or don't?
So this is like a direct product?
So what do we mean by that? So think of it as vectors with k coordinates, such that in each coordinate there is a matrix of the corresponding size. The operations are done as follows. We add and multiply coordinate for coordinate. So we add in the corresponding coordinate, and we multiply the corresponding coordinate. So this is what we mean by this notation. So, say, so there is k of them here, and here is a matrix from M and 1, matrix of M and 2.
Oh,
so you have a vector. You can think of it as a vector. Say, suppose you have a matrix A and 1 from M and 1 of R. Here will be A and 2 M and 2 of R. And operations are done as follows. If you have any two such vectors, then you add them by adding corresponding matrices, and multiply also by multiplying corresponding matrices. So that's what we mean by this direct product. I was taught by a famous mathematician that I'm not supposed to say direct sum many years ago for categorical reasons, direct product. But I also heard another, only slightly famous mathematician who says direct sums. So I don't know, maybe either one of them doesn't know category theory or so. So in other words, half of our paper said direct sum and half a direct product. So because we I guess haven't decided. So recently it's been direct product because we want to be prim and proper. And so is it clear what this object is? Okay. So now example 3. And if F is an infinite field, then the smallest number of generators of this direct product equals 2 if some size is at least 2. So over an infinite field we have this result. So this was done with say Sitki and me, I mean among other things. So this everything here is a joint work with my two friends. Write their names. And he's University of Binghamton. He's from University. And this is Alkravchenko. And he is now at UT Austin. Now things will get soon more diverse because here we get just one answer 2. Okay, so let's see how can we diversify this. First, let me write down another formula. So the smallest number of generators of direct product So what do I mean by this? So each term is a direct product of mi copies of this ring. So and then I take direct product of the resulting ring. So product. So this is a product of the same ring, mi times, right? And then I take the product of the resulting ring with all the algebraic operations. So this is the maximum of the smallest number of generators of So in other words, here of course we assume that all these ni's are pairwise distinct. So in other words, it's enough to focus on the matrices of the same size, direct copies of a matrix ring with itself, because then you take the maximum and so where things start getting interesting is the following. If you look at smallest number of generators fm of z to the k, then this is infinity. So that's why we decided to study what can we say more concretely. Why is it infinity? What happens, you say if something generates this ring, if we reduce modulo 2, then the same must be true, but for modulo 2 it goes to infinity by pigeonhole principle. So very simple combinatorial argument will show that. So we want to say things that are more precise and a little bit more. So,
can I ask a
yeah,
question?
sure, absolutely.
So your example 3, I got lost a little. So here, suppose this product, right? This
Right.
product has only one only one element. Maybe
Only one element, just
M3 means matrices 3 by 3 matrices.
exactly, yeah.
And so you're saying that the smallest number of generators for 3 by 3 matrices is only 2?
Exactly. So in fact, when I was postdoc at Texas A&M, it took me about 3 months to find such pair.
Can you
So,
show us?
so absolutely, yes. In fact, I have infinitely many, you see, as you noticed on pairs of matrices generating matrix algebra. So finally I found it at a boring New Year's party. Let's see, there are in fact many of them. Let's see which one do we like more. So for example, write this pair. So suppose you have matrix AX, which is where we understand this modulo n if we spill over, we reduce mod n, and y is E11. So they generate Mn of z. So it turns out that this construction is secretly sitting behind many proofs. In other words, there is the best available algebraic geometry, commutative algebra, and combinatorics. But that plus the space propels everything. In particular, in my paper with Said, we find these generators explicitly, in fact, it's at the end of this paper. So we have them explicitly for the field of rational numbers, but it's true for any infinite field. You just replace rational numbers with. So yeah, it's true. And we have in this paper infinitely many pairs. So that's what we've been playing with.
There's not only strange, it's more than unexpected.
Oh, thank you very much. In fact, I started looking for that pair when I was finishing my PhD. I was offered a summer teaching job and I refused it, so I was thinking about it. I got a postdoc, I was also thinking about it, and finally I found it. Yes. So, there are many such results. So in other words, in group theory, what I don't know yet, and I would appreciate education, is the following. While we obtain all kinds of formulas, and I'll start showing things without proof because I don't want to abuse the generosity of your time, I don't know any connections yet to generating set with, say, other areas of mathematics, generating sets of rings of these matrix rings. So formulas are pretty, I don't know if, so I'll show you formulas in a moment. Same pretty, maybe they're not, maybe you won't find them as such, maybe you will. But I would really appreciate if we could, if you could educate me, if you would see a connection to some other areas of mathematics other than the question being interesting, generators being fundamental, so forth. That's right. So I'm curious what would be such a connection, and since I'm in reasonably good health, if you contact me in 5 years, it's fine. You know, it doesn't have to be within a minute or so. Now, I was thinking, let me write down some, so in other words, I have things prepared in sort of reasonably orderly fashion, at least it looks like that. So if I start running out of time, I'll just write the formulas, is that okay? Because I think the results triumph over structure. And so, now, let's introduce the definition too, because so Said Sipki and I introduced it in the same paper when we did this. So at the time it was a pure curiosity because we couldn't say anything about the sets at all. Suppose you have this. This will be ordered m tuples of n by n matrices. such that this generates as an R algebra. So if we cannot solve the problem, at least it's good to give it a name. So, so we know that we knew at the time that many of the sets were non-empty, but what else? Aha. So example 6. So if F is a normed field, then the set is dense in of F. So all this was also done. Now, what about finite fields? For finite fields, it turns out that we used, three of us used Loomis-Whitney inequality. It's a beautiful inequality, it has nothing to do with finite fields. And we obtained the following estimate. So for finite fields, we don't have any topology, but we have combinatorics, right? We can say something. So I'm going to write some formulas. There is a philosophical consequence from it. So please bear with me as I write it. So this last term is the size of these all possible set of all possible such tuples. So the consequence is that as you divide out by this term, you will see that asymptotically these two numbers are close to each other. So in other words, let it be our first theorem. So this goes to 1 as q plus n goes to infinity. Well, this is an asymptotic result, but we also have exact formulas. So there is an obvious one, gm1 of fq is q to the m minus 1, because only we need to rule out the zero vector. And there is another one that made us even more exciting, gm2. There is this formula, q to the 2m, q to the m minus 1, q to the m minus. And we also have the formula for g, the size of gm3 fq. This is more complicated but explicit. And now we had the following dream. So this is the dream. Suppose you do the following. Suppose you do the following black magic and witchcraft. Suppose you write, say, p to the m minus 1 and you divide by p to the m, right? Well, from the point of view of pre-calculus, I don't think it will be worth too many points, but for us it was a revelation. Why? Because if you multiply all these factors, you get the zeta value. Multiply over the primes, right? Of course, at the time we didn't have any proof that this is not strange. So, okay. And here we decide to do the following. So suppose you do this p to the 2m, p to the m minus 1 minus p, and you divide by p to the power 4m, right? See what we're going to get. You're professional calculus teachers, right? At least. You had to teach all calculus, not a single one here. Anybody not teach? Don't think so. Sorry for being so presumptive. So 1 minus 1 over p to the m, right? Is that how it goes? 1 minus 1 to the p to the m minus 1. And then when we had this guess that was very wide and unproven, that if you multiply this over all primes, you're going to get zeta values, right? You're going to get zeta values, and zeta values are pretty, so therefore we're going in the right direction, even though when I suggested during one of my talks many years ago, let's say people politely questioned my sanity. And yes, it takes time to prove, so all of this and more is proved here. It's like how many pages? Some pages. So in other words, you understand that, so let me repeat. So suppose you take the product of all primes. So what is this? 1 over what? What should I write here? Zeta of m, right? Well, zeta is Riemann zeta. Is that good? And if I take the prime product over all primes of this, I'm going to get 1 over zeta of m minus 1. So this is a known fact. In fact, if I were to make a science fiction movie about Euler, the people wonder why he studied zeta function. It's not clear. He studied because he studied. I think he must have known the probabilistic fact that the probability that, say, choosing 3 integers at a relatively prime is 1 over zeta of 3. That's why he studied. That's why he summed 1 over n squared. Again, in calculus books you'll see, because he was very, strong willed. But that's, I mean, brilliant mathematicians that don't study stupid questions, right? Why would he be just summing the series for no reason, right? I don't know any other reasons why he would sum it. So, and now we started believing the following, that the probability that M random 2 by 2 matrix is generating the ring M2 of Z equals this value. It's not a proof, and so suppose you choose 3 matrices, right?
Yeah.
Then your chances of generating M2 of Z will be 1 over zeta of 3 times zeta of 2.
Okay, fixed. So
You fix M.
this is a fixed Q, M, and N.
Yeah, right. So I look at prime number. Suppose I go from finite field. Suppose P, so here P is a prime integer. 2, 3, 5.
Yeah.
So that was the belief that sustained the project for a few years. It turns out that all of this is actually correct. Not only we have theoretical proof, we have similar results for 3 by 3 matrices. Not only that, we had the privilege of an undergraduate student at my previous university. She later went to study for PhD at MIT. She did some numeric simulations to confirm those probabilities experimentally. How would you do that? You can, so how do they do Monte Carlo number theory? They choose matrices whose entries are at most something, right? And then you form the proportion, and you see if that proportion is close to the numeric value of the quantity that you claim is true. As you expand your boxes, and so we have experimental evidence that this is no nonsense. And again, now let me write down some other facts, if you don't mind. Is that okay?
I have a question about
Yeah.
this theorem that I'm still thinking.
All right,
Still
yeah.
stuck
Ah,
on this
yeah, yeah.
theorem. I want to say that this is a particular instance of an appropriate 0-1 law, and the main content of the theorem is deciding whether it is 0 or 1. Am I thinking of the right thing here?
I'll be delighted to talk with you about it, because I always study questions about which I don't know anything, as you know. In particular here, we had to learn so much mathematics. This was not what my PhD thesis was about, or one of the two, I guess. So if you have any such thoughts, I'll be delighted if you could share them with us, because we're looking to understand more. You see what I'm saying? And if, let me write a couple more results. Maybe they will bring even more and further analogies, and we will be delighted to learn. Speaking of probability theory, of course, what motivated us, I heard Albert Chiraev's talk at Stiklov Institute, so he's a student of Kolmogorov, and so more important than all his books was the following revelation. Suppose probability theory does not apply completely, right? But applies, it's my interpretation, so he said more dignified language. Suppose it applies 97%. Then you want to use 97% because you know what? You are going to make big progress. So this was our motto. So if probability theory does not apply completely, use what applies. And in fact, we'll be delighted to learn more. And if it's a, you see what I'm saying?
Yeah.
We do not own the subject. Now I will tell you one paradoxical thing. You can say, what about m equals 2, right? What about m equals 2? We have zeta of 1. So for these purposes, we believe that 1 over zeta of 1 is 0. It's not true for zeta function, for this application of zeta function, which means that the probability that a pair of matrices generates m2 of z is 0. Such pairs exist, but they're very sparse. Okay, now there is something that I find black magic and witchcraft. So I just said that a probability that a pair of integer matrices generates m2 of z is 0, right? What about pairs of random integer matrices generating 3 by 3 integer matrices? Do you think it's more likely or less likely to generate? So if you were to bet your money, so how would you bet random AB generating M2 of Z? Or AB, CD I guess, CD generating M3 of Z? What do you think is more likely and by how much?
You already gave away that this is paradoxical.
Yeah, it turns out that this is much more likely. Is that okay? All right, what are the chances? Here, the chances are not so terrible. Verifying that you succeeded will be terrible because it's actually hard. Computation. If someone gives you a pair of 3 by 3 integer matrices and asks do they generate or they not generate, I mean, of course, if someone gives you 2 simple matrices, it's easy, but if it's not simple, in fact, it's not that easy, and we have an algorithm in our paper. Okay, so here, 1 over, so what are my chances? 1 over zeta of 2 squared times zeta of 3. So about 30% here. And nothing here. Well, why nothing here? Because this can be described as follows. Determinant AB, it turns out minus BA should be plus minus 1. It turns out that that's enough. These are, of course, hypersurfaces, and they have density 0. There is the structure of the generating set is more complicated, and it turns out it's pretty dense. So 30%, we can go for it, right? I mean, it's not exactly 30%, but it's close, if you substitute all the values. Okay. Now, what are other results that we have? So these are probabilistic results. But we also have exact algebraic results. Is that okay? I'll draw a couple of graphs just to illustrate what we have. So, and it turns out that the two things are related to each other. They're not just two separate sides of the subject. It turns out we use some of our probabilistic calculations to prove the table that I'm about to display with exact numbers. So, if I may, I will erase here. Is that okay? I will draw two graphs for your attention. So, one of the graphs is this graph. So, this will be the graph of the smallest number of generators of the ring M2 of Z to the K. So, okay. So this is my K-axis, and this is the axis of the quantity I'm after, right? Smallest number of generators, M2 of Z to the K. So it turns out, suppose we have 1 here, and then we have 16. And it turns out that this is 2. So from 1 to 16, the number of generators is 2. Then, after 16, it jumps and becomes 3, and I will not draw to scale, I will write 448. So, yeah, most number of generators. Then it again jumps by 1. How do we know it jumps by 1? It turns out it's not obvious at all. We use these matrices to prove this theoretical result. That actually jumps by 1 and not by some other quantity, right? Because it's not clear why it should jump by 1. It turns out it always jumps by 1 when it does. So here we have 4, and number 4 is just a little bit bigger. It's this one, 8960, and I'll write another one because 5. So these steps get larger and larger. And this one is 158720. And it continues. So we have formulas for exact cutoffs. So it's step function where steps become ever so large. We also have a similar graph for 3 by 3. And the steps are bigger. So this will be the graph of smallest number of generators of M3 of Z to the K. So 7, 6, 8. So number 2. So from the 2 by 2 matrix up to 768, we have 2 generators. 769 has 3. And I don't know how to say these numbers. Well, this one I still do, 660. 480. Next one I will have difficulty saying, whatever that is. So I'm going to write it. The only reason I make room, I don't want to fit all the. I want to fit all the digits. 3, 8, 8, 9, 1, 5, 2, 0, 0. And the fifth one is okay. 992. So these steps become bigger and bigger, but they continue doing, they do this pattern. Now, we prove the existence of those generators. In some small instances, we can display them explicitly. And in other cases, we prove that it's actually true. So these are the smallest number of generators. I don't think we'll be able to display that. Let me write down a number theoretic statement. Now, when I talk about probabilities, what we also prove is the following. You understand that in a free abelian group, you can put coordinates in many ways. You can choose basis, you can have another basis. So we prove that these numbers and corresponding number for 3 by 3 matrices are independent on how you choose the basis. So what do I mean by that? So how do we understand probability? Asymptotic density is not an honest probability, but it's almost. So many low probabilistic phenomena apply. So how do we know that every other integer is even? So you choose sufficiently large symmetric interval, count the number of even integers, right? Send the ends to infinity, and the ratio will be 1/2. So in higher dimension, you start choosing boxes, right? Finite boxes, and a finite box you can count everything. You form a proportion, you send the size of the box to infinity. That's what we mean by density. So we allow for any choice of coordinates. So for any choice of coordinates, the numbers will be absolutely the same. I will skip over a few details. I will write a statement, probably one of the key number theoretic facts that we discovered as a result of working on this project. We have to improve the result of Björn Poonen from MIT to do that, but we had huge motivation because we had lots of experimental evidence and conjectures that we wanted to settle. So his paper was extremely important to us because we now had a hope that something is going to work out. So it's called Theorem 3 in my notes. My apology for not numbering things consecutively. I skip over many steps. I'd rather go slowly and clearly rather than just rattle things at a great speed. So let f1 through fm be polynomials with integer coefficients in some number of variables, x1 through xk. Now let's look at the set of those k vectors with integer coordinates such that the corresponding values of the polynomials fm of a equals 1. Then the following is true. The density of this set equals the product over all primes 1 minus over p to the k. So let me explain what I mean by all this. You understand that you can reduce, so here p are prime numbers, p prime numbers. So if you treat your polynomials with integer coefficients modulo p, you can look at the number of simultaneous zeros modulo p. Let me illustrate this in a particular case. It's actually an extension of a classical result. Suppose I will let so here's an example. Let k and m be 2. Suppose the first polynomial f of x1, x2 equals x1, and the second polynomial f of x1, x2 equals x2. Okay. Then our set S is the set of relatively prime integer pairs a1, a2, and z, such that GCD of x1 and a1 and a2 is 1. Okay. Now, I'll ask you another question. You teach calculus, so you know. So how many solutions does this system have? How many solutions? With this system, how many solutions?
System? Not many.
Exactly, but what's the famous number? How many you think?
This is in 2 dimensions?
One.
Yeah, 2 dimension.
There is a solution.
Yeah, so how many solutions then?
One.
One, exactly. This is only one solution, is it clear? Okay, it has one solution. Now I'm calculating the density. Oh myself, as follows. It's the product over all primes, 1 minus, and each of those numbers is 1. It's how many solutions does the system have modulo p. For any p, it has only one solution, right? So 1 minus over p squared, and this is a famous quantity 1 over zeta of 2, where zeta is the Riemann zeta. So the density of relatively prime pairs is this. So this is an extension of this result. The polynomials that we get in this project are so big that we never even display them. We know that they exist. I mean, it will take, I don't know, how many pages for this. So display them. So we approached our question indirectly, but this is what we have.
So what is this number of v? What is v?
V. So v, since we want to be fancy in arithmetic geometry, say variety. So in other words, it's the number of solutions of the system modulo p. Number. Since in this particular case, so even in this particular case, we get something of interest.
Of solutions of you wanted to make it 0 or you
Right, exactly. See, my polynomial.
Number of zero.
See, these are my polynomials. I make them both 0, and I look at this mod
okay.
p.
So number of zeros in the variety.
Right, and so number of zeros mod p. And in this case, that number does not depend on p. There are many cases when it does. However, for purposes of illustration, why not? Even when it doesn't, it gives something of some substance. In fact, my understanding is the first person who calculated this density was the first person of the records I could get to was Dirichlet, because I saw it in his collected works. So he calculates this density. So, and well,
So this formula is due to Divination?
no, this formula, actually, I can say proudly, I think this one is due to the 3 of us. It's our formula.
Bogdan, maybe you need a homogeneous condition on the polynomials?
It turns out no.
No?
It works as it is. It's pretty resilient. So why could we prove it? Because we looked at some earlier, not very well known results of Alexander Ostrovsky from 1920s, which didn't make it into, not too many textbooks, I would say, have them. So we had someone very powerful on our side. Because otherwise it would be very hard to imagine. So Bjorn Poonen proved it for 2 polynomials without a common factor. Now, in our case, we don't know whether our polynomials have a common factor or don't have common factor. We don't know anything about those polynomials. We know they're huge. So we could not make any assumptions on them. So either we have that and have our results, or we don't have that, and all of this becomes at the level of fortune telling, and numbers look pretty, or maybe they don't. You understand that there are all kinds of such claims that are actually erroneous, right? You know, there's some pattern that doesn't hold in fact. So the techniques that we use, we reduce modulo primes, we study what happens over rational numbers, and we somehow paste it together. There are also theorems. The first one was written for us by Henrik Lenstra, and we use it to put data together to get these tables, for example, because we know what happens over finite fields. Say if I reduce my matrix over and the question is how to do it. Globally we need Hendrik Lenstra, so they are not published anywhere before, so we have his results included, and we in fact improve on one of them, but without him we wouldn't probably start. Let me give you some, it's okay, I'll give you some thing that will seem crazy to you, but it's actually true. So it's about basic algebra. So suppose you have several elements that generate this ring. This would be matrices 0, 1, mod 2. Now, so this is the witchcraft. Forget mod 2. Treat them as usual integers. It turns out I will generate them 2 of z. This is only true for 2 by 2 matrices. It's not true for any other size. So, the first time we saw it, we suggested it, we received comments full of doubt, and okay, this is true. So John Tate, he was 82, he told me in his office in Texas that right, you may be lucky. It's actually true. It's true.
Say it once again.
So suppose you want to generate this guy.
Slowly.
Suppose you want to generate this guy.
Yeah.
So what is this? 0, 1, mod 2.
0, 1, or 2?
0, 1, mod 2. 0 and 1. So F2 is a field with 2 elements. 0, 1, mod 2. Suppose you generate this finite ring. So you have several vectors that do the trick, right? And now you do something unthinkable, something that seems breaking all the rules of engagement. You say, you matrices, forget that you are modulo 2. Now you are 0 and 1 as ordinary integers. You forget about their modular nature. And now you treat those elements as being part of M2 of z to the k. Because they forgot, they denounced their heritage, right? No longer modular we are, right? So, and they made those matrices who forgot about their modularity will generate this one. It's totally false for all higher sizes. So for 3 by 3 it's false. We don't know about higher sizes because already 3 by 3 took us some effort. This is something from the life of 2 by 2 matrix. I thought I'd tell you. I don't think it's not necessarily as well known as some other facts about matrix. The work is of course done over orders and number fields. However, I reduced everything to integers today because I think that if the work is meaningful, it should tell something meaningful about the basic examples. Because if I were to talk about no orders and number fields, you would suspect that I'm in fact doing something superficial and trying to fool you with abstract notation, right? Ramification theory, what else? So, in other words, this is done in greater generality, so we decided to specialize today just to high school integers. Thank you very much.
Do you have any other questions for Bogdan? Do you have, by the way, do you have some little theoretic reason why you have this kind of steps or some width relation?
So here, in fact, we calculate what happens for the field of 2 elements. And now we use this lifting property.
Okay.
And here we use, what do we use? So we use, pretty much we use algebra over a field with 2 elements. Here, a little bit more difficult. We cannot just appeal to a field of 2 elements, so somehow we have to bundle the information about all the primes. And actually, yes, there are a number of theoretic reasons, but what's interesting, there are many. So it's almost like you have several lines of inquiry and then they converge to something. Okay. So in other words, don't want to be evasive. So in other words, it turns out that indeed several, so in other words, that's the best I can say, that several inquiries luckily converged into one point. So, as John Tate said, you can be lucky, so we're lucky.
Okay.
Right? So we're lucky. But on the other hand, if someone has any questions, you know, it's all online and it's all available. In fact, speaking of which, it's not that easy. How would you, so let me ask you a silly question. Suppose you assign this exercise in your algebra class. Suppose you have a pair of 3 by 3 matrices. How do you know that they generate on 3 of z? Would not be that easy, right?
Very difficult.
Computer and calculator.
Computer, yes. So, but how would you arrange that on the
It's
computer?
not going to be decidable on computer. I'm sure it must be undecidable.
So what we do is the following. It turns out that thanks to, even though the estimates is imprecise, there is an Israeli mathematician Azaria Paz who actually bounds the number of monomials we need to check. That's the first. It's a big number, so by hand checking it would be, it's worse than punishment. So what you do, you take all these monomials and flatten them as vectors. And you generate a matrix, say, of huge size. Then, speaking of Lenstra, his brother, and Laszlo Lovac, you apply LLL reduction to it. And then you get a nice 9 by 9 matrix all of a sudden, for example. And about that matrix you can say lots of things. So in other words, by hand we wouldn't know how to do it, but we have 2 algorithms on our side. And Azaria Paz thanks Lenstra for helping him on that paper too. So in fact, so in other words, that would be very hard, even for 3 by 3. For 2 by 2, now we know it's not hard. You calculate term into the commutator and decide what's plus minus 1, you're done. But for 3 by 3, it turns out there is no square matrix that tells us. It's highly non-square, and so while it could be that Paz's estimates could be improved, no one, as far as I know, at least I haven't seen anything. So in other words, the idea is how many monomials to check, right? Because in principle, if the degree is not bounded, it's undecidable, we would run out of steam, right? It turns out that he bounds how many monomials do we need to get involved in our game. And this number is independent of matrices. So it depends only on number 3, the size. So once you have monomials, then you can approach to the computer, but we need the bound. And so, so that's what I had the privilege of teaching that student who went to study at MIT for computer science. So, and then she married Gap and Java. So Java generated pairs of matrices, and Gap, the famous program, would implement the algorithm. So without her, we would be at a loss as of today whether we would even believe the results. So now, she didn't get zeta values. You understand this is a rational number, you can get fractions, but close enough. And she's one of the most trustworthy people I've met, and I looked at the code. So to the best of my knowledge, I can say that she did a good job of it. So,
I'm trying to think about this business of deciding whether you've generated 3 by 3 matrices and how this bound would come. Does this bound come from some like Diophantine characterization of generating?
It comes from, well, the reason that these bounds are not really strong, it comes from really Cayley-Hamilton, repeatedly applying Cayley-Hamilton. Seems to be the only thing that's available. So we cleverly apply Cayley-Hamilton, and that's how we get a bound. We do not get an optimal bound, but at least we get some concrete bound of which we are assured that.
Yeah.
So the papers that I've seen apply versions of it. Cayley-Hamilton and sound very cleverly in the algebra. And how clever, like, when I read those papers, I understand that I don't know linear algebra at all. Because, I mean, they find facts that I've never seen, and yet the bounds are not optimal, so for large numbers. But they get concrete bounds. So you see, that's as far as I'm concerned, it's amazing. If not for them, we would not have experimental evidence. And you would say, yeah, 50 pages, and you can write all kinds of nonsense, and how do we know it's correct, right? So I would say, well, we have codes that can be run. Of course, one can say, what have you checked the background code? I mean, these are legitimate questions, but within that, we have verification.
Yeah, so I'm less worried about that. Trying to think how you would get that kind of bound out of Cayley-Hamilton. I don't care how many times. How does Cayley-Hamilton give you a bound on how far you have to look for generation?
So this is the paper. So where's Azaria Paz? Yes. An application of the Cayley-Hamilton theorem to matrix polynomials in general variables.
Okay.
So in other words, this is a beautiful paper.
Okay.
So in other words, you would think indeed, what can you get out of Cayley-Hamilton? After but in his skilled hands, and he has very few papers actually.
Okay. So they do it somehow.
So in fact, it's not a long paper. It's like 9 pages long.
Okay.
So I owe.
Was that the dimension of the matrix 9 a while ago?
What was I saying?
You had 9 by 9 matrix a while ago, so I was thinking joke.
Oh yeah, no, that's great. That's great. I think that mathematics should lead to good mood and jokes, because otherwise, if this activity is bad for our health, then why are we doing it? I mean, why shorten the already short life, right?
I hope you were joking now.
No, in fact, I think that mathematics, in some instances, I think prolonged my life. I was in situations where I needed a painkiller, and this paper provided that beautifully, because at the end of the day, it's a situation where no advice, in other words, one can always help that in one's life, where the situation where you cannot do anything, right? There is no help, there is no advice, it's like, do whatever you can. So this is a very good, so as far as whatever I am now, I owe it to matrices. I say mathematics has no applications, I have normal blood pressure, so it's good for health.
So, thank you, speaker again.